Hey everybody. So we're now looking at how we can use pedigree charts to actually analyze the inheritance of a certain gene. So we've learnt lots about drawing pedigree charts and how to identify which person has a trait and which person doesn't. Now we're going to use them for what scientists actually use them for figuring out the genotype of particular people in the family and for predicting the phenotype and the genotype of children further on in the pedigree. So the first thing we need to remember is that we've now learnt about two types of genes. So remember that genes can be found on the autosomes, the normal chromosomes, or they can be found on the sex chromosomes. So the names we give those are that genes can be autosomal or they can be sex-linked. Okay, well, as well as that, we remember that traits can be dominant and recessive. So that means there's actually 4 types of inheritance for how genes can be passed on, from what we've learnt so far. So we'll draw a quick two-way table to show all 4 situations. So a two-way table is just like a pedigree chart, a Punnett square. So you can have autosomal genes, you can have sex-linked, you can have dominant traits, and you can have recessive traits. So putting those together, you can have an autosomal dominant trait, you can have an autosomal recessive, and the same for sex-linked as well. You can have sex-linked dominant and sex-linked recessive. I'm ignoring the fact that you can have X-linked and Y-linked. I'm just lumping them together. But we could talk about X-linked. And actually, when I say sex-linked, it's better to think of it as X-linked, because Y-linked, they have their own pattern of inheritance that we haven't talked about, but it's actually a lot more simple, because since there's only one copy of the Y chromosome, and males are the only ones that have it, that inheritance is quite simple. But for now, we can see there's actually 4 types of inheritance, and to start us off when we analyze our pedigrees, we're going to only focus on autosomal inheritance. So dominant and recessive, and the goal of analyzing a pedigree chart is basically to figure out, looking at the pedigree, is this a dominant or is it a recessive trait? So here's a couple of examples for how to prove it for sure. So if you see these situations in a pedigree chart, you can definitely identify if it's dominant or recessive. So the first one we'll say is proving dominance. So proving whether a trait is dominant in your pedigree. Okay, so if you see this situation with 2 parents that are affected by the trait, and they have a child who's unaffected, this has to be dominant. So 2 affected parents have an unaffected child. As soon as you see that, it has to be dominant. So remember that, but also let's explain how we can prove it. Well, it's best to think of it the other way around. So if this condition was recessive, that means that the mother here, she would be homozygous recessive. Let's just use A's for this gene. and the father would also be homozygous recessive because he's affected as well. This child here, this boy, he'd be homozygous recessive. But the parents, but this child here is unaffected. So they've got a big A allele, a healthy allele from somewhere, but that's not possible because both parents, you can see, if this was recessive, both parents can only give their recessive allele to their children. So it's impossible for a child of two affected individuals to have a healthy child. So in other words, let's have a look at this situation as it actually is. So the mum's affected. It's a dominant condition, so she must have one dominant allele, which is the big A, that's giving her the condition. The father's also affected, so he must have a big A. This child here, well, they might have got both big A's from their parents, one from each, or they might have only got one. And then this child, they must have two copies of the healthy recessive allele. And that's possible because both parents here are heterozygous. So the mum can donate her small a and the father can donate his small a. So that's the only way for two affected parents to have an unaffected child. They're going to have to be both heterozygous and the trait has to be dominant. Okay, so our reasoning there is that if it was recessive, two affected parents can't have a healthy child or have an unaffected child. We might not be talking about a disease, so they're just not affected by whatever trait we're talking about. Okay, well, we can also prove a recessive situation and a recessive trait. So proving recessivity. And that's if you see this situation here. So two unaffected parents, if they have an affected child, it has to be recessive. And it's a similar line of thinking to before. So again, let's talk about the opposite case. Why can't it be dominant, this trait? Well, if it was dominant, then this child must have an affected allele. So let's say they have one. They've got an affected big A, and then they've got a normal small a. Well, they must have got that big A from one of their parents. So let's say they got it from mum. But that doesn't work because if mum has a big A and this trait's dominant, she'd be affected too. And the same with the father. So if a trait's dominant, you can't have two unaffected parents giving it to their child because that affected allele is going to affect the parent and it would have affected their parent and so on back every generation. So this situation has to be recessive. So in this case, our reasoning is if it was dominant, two unaffected parents, they can't possibly have an affected child because none of them have that dominant allele causing the disease or the trait. Okay, so then that means let's look at the real situation here. This has to be a recessive trait. So then the affected child, they have to be homozygous recessive, small a, and that means they must have got a small a allele from both parents And since both parents are healthy, they also have to have a healthy big A allele. So each parent here is going to be heterozygous, and that means their son here, who's also unaffected, he could be big A, or homozygous. Sorry, or heterozygous, big A, little a. Okay, so if you see these situations, you can definitely prove whether a trait's dominant or recessive. But you're not always that lucky. Sometimes you have to just use probabilities. So the final thing is really a trick to use, or it's more an assumption. So a useful assumption to make. And the assumption is, if you see the trait in every single generation of a pedigree, you can normally assume that it's dominant. So if a trait appears in every generation, we can assume it's probably dominant. Not always, but probably. And the reason for that is if the trait keeps appearing in every generation, then that means people that are marrying into this family, every single one of them has to be a carrier, which is unlikely. So the mum back here in the very first generation, she must have been a carrier to pass on a recessive gene, sorry, recessive allele. And then this father here, he must have been a carrier because two of his children have that trait. And then this mum, she must have also been a carrier. And then this father must have been a carrier. And it's unlikely that that many carriers join the family, just because recessive alleles are not often that common in the population. But of course, like everything in biology, there's exceptions to the rule. So we can't be sure. This could actually be a recessive trait, but it's more likely that it's a dominant allele being passed on from one generation to the next. Okay, so that's how we problem solve using pedigree charts to prove dominant and recessive traits.